Hello, in this video we are going to talk about our senior project, which is an autonomous lawnmower for Duke Energy's solar farm. Solar farms are an unobtrusive and effective way of generating electricity by converting sunlight into electrical energy, and the more sunlight hits the panel, the more power it will generate. Any obstruction near the panels can affect the efficiency of the panels to generate electricity. So it's important to have ground maintenance service when owning a solar farm, because grass and weed can grow beneath the solar panels and around poles where weed tend to dense and hard to reach with conventional big lawn mowers. The aim of this project is to mow all areas beneath the panels and areas that are hard to reach using a small lawn mower that will operate autonomously. This device will also reduce the ground maintenance service expense. Here is a list of requirements that our device must accomplish. It should cut all the grass in all areas identified and avoid obstacles that get in the way. It must complete areas 10 by 50 square feet within 15 minutes at length of 3 to 6 inches. The height of the lawnmower should be less than 20 inches. The lawnmower should be equipped with a remote control kill switch.
To begin the process of selecting materials for our mower, we first started with the sensors. We chose to use a LiDAR sensor, magnetometer, and ultrasonic sensors to detect objects in our path. We then used equations for torque to find the correct motors that we would need to set our mower in motion. We then selected other components that would make our mower fully functional, such as motor drivers and the trimmer head. We then had to select a microcontroller that was powerful enough to handle all of these inputs, so we chose to use a Raspberry Pi. We then analyzed all of the circuits and data sheets from sensors to find the correct battery that we would need to power our motor throughout the cut, and we chose to use a 12-volt, 10-amp-hour lead-acid battery.
This is an overall view of our subsystem. The microcontroller that we chose for this project was a Raspberry Pi 4. My teammate Yahia will go into further detail about our reasoning behind this choice and its benefits later in the video. We also utilized an array of sensors, which are all powered by a 12-volt battery. This battery also provides power to the Raspberry Pi microcontroller and the trimmer head for cutting grass. The perimeter wire sensor and generator work together to prevent the lawnmower from leaving the specified mowing area. The signal generated is connected to boundary wires that are placed along the specified mowing area. It subsequently generates a signal along these boundary wires. The sensor located on the AutoLawn lawnmower detects this signal and relays its analog output to the microcontroller. Due to issues with procuring an analog to digital converter, an Arduino Uno was programmed to read the incoming analog signal and output a digital signal to the Raspberry Pi. Our primary sensor for object detection is the LiDAR, around which our other sensors act as secondary sensors. So what is a LiDAR? LiDAR stands for light detection and ranging. In this device, a laser beam is emitted from an emitter located on the LiDAR. Consequently, the emitted beam is reflected off an object and detected by another sensor located on the LiDAR. The primary method of calculating distance is through the time delay between emission and sensing of the laser beam. This time delay, in correlation with the speed of the emitted laser, allows us to measure the distance and detect the object. In the LiDAR we chose the Y-LiDAR X4, created by Y-LiDAR. There is a rotating component that detects and emits the laser beam. The LiDAR has a motor which spins the component at 360 degrees, allowing us a wide scope of detection. We chose this specific LiDAR for its accuracy as well as its 10-meter range. This range will allow us to detect objects well before we run the risk of collision.
So to control our overall system, our group has elected to use a Raspberry Pi 4 Model B. And choosing this device was based on the amount of sensors we had and the need for us to constantly be measuring data from these sensors without actually interrupting our motor process. So for example, if every time we wanted to decide what to do for the motor, we had to wait on a response from the LiDAR sensor and the perimeter sensor and the orientation or accelerometer gyroscope sensor. We would be slowing down our program immensely trying to measure from these at the same time if we're doing it all in one script. So early on we realized that we would have to either, run concurrent scripts running at the same time or, have some sort of threading or multiprocessing going on, which just isn't available in typical microcontrollers like an Arduino or a PIC. So we started looking at, onboard computers like the Raspberry Pi, which has those functionalities allowing us to, run concurrent scripts. So this led to us, picking the Raspberry Pi just so that we could manage data from all of our sensors without actually interrupting the speed at which our microcontroller makes decisions. And the only downside to the Raspberry Pi that we had to account for was its lack of an analog to digital converter. And we needed one for our perimeter sensors, which would effectively input analog signals based on how close they were to the wire. And we would need a way to convert that to digital to actually be used as data by the microcontroller. So to circumvent this, the only thing we had to include was we also have an Arduino on our system, which is basically only functioning as an analog digital converter and is communicating serially via a USB port to the Raspberry Pi. So the perimeter sensors go to the Arduino, converts the analog signal to a digital one, and then sends that information to the Raspberry Pi, where it's effectively just another mode of information. The LiDAR sensor is also connected serially to the Raspberry Pi, and the orientation or accelerometer gyroscope sensors are connected via I2C to the Raspberry Pi. So all of our code for our Raspberry Pi programming was written in Python just because of its high level of abstraction, making it easier to, find a library for our sensor, download that library, and begin interfacing with that sensor easier. Our Arduino, since we're using an Arduino for its analog to digital converter to measure our perimeter sensors and send it to the Pi, we had to write a small script in the Arduino IDE. But other than that, all of our programming for the Raspberry Pi was done in Python. Our main script was essentially 3 separate scripts actually running at the same time. Earlier on I stated how it was important for us to be able to run these different scripts at the same time to, make the full use of a full processing power and be able to have a system that doesn't have any lag or responds accurately and in a timely manner to stimulus from the environment. So 2 of those scripts one of them is for the LiDAR. So our LiDAR is constantly measuring distance at key angles and recording them to a text file. And then our second one is from our perimeter sensor. Our perimeter sensor code is constantly communicating with our Arduino, and based on what the Arduino is telling it, is writing the perimeter sensor values to a text file. So we have multiple text files based on the actual angles of the LiDAR, like, the distance directly in front of the robot at angle 180 is constantly being written to a text file, whereas at a different angle it's being written to a different text file. All in all, we probably have around 7 text files constantly being written to by these 2 scripts. And then our main navigation script is our last third script. And this script is kind of telling the motors in which way they need to move based on the information from these text files. So this main script is constantly reading from these text files, and based on, these values, they can decide in which way the robot needs to do. Does it need to adjust its angle? Does it need to change its heading? Does it need to circle around an object, turn 90 degrees, 180? All of these are different cases based on the sensor inputs. So this here is our robot, and this video is going to showcase what happens when it encounters one of our perimeter wires. So as you can see here, it actually just hit one of our perimeter wires and it's now doing a 180-degree turn. And basically every time it hits the wires on that front sensor, which you can see that little capacitor sticking out, there's our front sensor, it'll do a 180-degree turn. These capacitors basically output an analog voltage based on how close they are to these green wires, which are perimeter wires. These green wires are basically copper cables that have an alternating signal running through them, and the capacitor just basically picks up on any current generated because of these signals. So right here, it's actually going to hit the wire again, and it's going to do another 180-degree turn, and then it's just going to keep going straight and basically keep doing the same thing. Effectively, what it's doing is that it's slowly, going down this whole array. So you see this array here, it's going to keep going down this whole array and mow everything inside of it. And this is going to keep hitting these sensors and rotating, and then just keep going straight. You see these little sweeps that it does? These sweeps ensure that it's traveling in a straight path so that it's mowing a perfect row down. And that it's not just, slight, things hitting the wheels or variations in the terrain, causing it to, sway or lose its trail and travel in a diagonal direction. So basically it just keeps going straight. It'll do a 180 and it'll just keep going straight again. And yeah, this is basically how our robot functions with our perimeter wire. So this video is going to demonstrate how our robot functions when it encounters an object. So as you can see, it was traveling straight and it just detected the object. Now it's doing a 90-degree turn, and now it's going to begin actually circling the object. So that, it's actually going to do a full 360-degree circle around the object, and then continue on another 180 degrees until it's on the opposite side. So the reason we do this is to ensure that we actually do a full 360-degree cut around the object, and not just as opposed to 180 degrees. So for example, we started here. If we only traveled 180 degrees around the object and then continued straight, we'd be missing cutting the grass of this whole half of the object. But this way, it ensures that we can cut all around the object and then also continue on the opposite side. So we entered from here, it was going straight, it encountered the object on this side. It just did a full 360-degree rotation. Now it's going to do another 180-degree, go to this side, turn again. So because it's going to be facing that way, turn another 90 degrees that way, and then continue straight. So we're actually going to see that soon enough. This cable is actually just, for the battery, which is way too large for this chassis. This is just, a prototyping chassis for our electronics. But you're going to see here that it's just, it's on the opposite side of this object now. And now it's going to go turn 90 degrees and continue on its way going straight.
To create the chassis, the measurements of all the components were taken to ensure proper fitting. These measurements include, but are not limited to, the motor shaft, the trimmer, sensor dimensions, and battery dimensions. After noting down the measurements, a 3D design of the chassis was created using Autodesk Fusion 360 and subsequently 3D printed in PETG filament. This specific filament was used for its high resistance to heat, which will be very useful during hot environmental conditions. The main part of the chassis consisted of holes just wide enough to fit a nut. The screw would then be pushed through the top and bottom portions of the chassis and secured with the nut to the main part of the chassis. The holes were placed equidistant from each other to prevent cracking of the PETG filament. The screw holes created had diameters of 5 mm to house M5 screws. A standard screw size was chosen for ease of assembly. The top cover and bottom portion of the chassis were not 3D printed. This will be explained further by my teammate Ron Blem.
To start the fabrication of our chassis, we first had USF 3D print the side walls for our mower. These came in 4 separate pieces, which I then used epoxy to glue together to make one solid piece. Because of the coronavirus outbreak, we were unable to get the finished product for the bottom and top, so we fabricated these pieces out of wood instead. We also had USF 3D print a case for our Raspberry Pi and holders for our motors.
It can be observed through our video that we have created an autonomous navigation system that is able to detect an object, move around it, and continue on its path. The AutoLawn also stays within the area specified by the boundary wire. As with all autonomous navigation systems, machine learning is an optimal method for object detection and avoidance. Machine learning-based components, such as the Pixie Cam, could also be used in conjunction with our existing LiDAR system to provide a highly accurate, self-correcting lawnmower. Thank you for watching. We hope you enjoyed our presentation.